In this lesson today, we're moving on to our next topic. So that is, we're now in topic 3, counting and probability. And the first lesson is sets and Venn diagrams. So our lesson is a pretty straightforward one, and it should be a review of some of the skills that we've worked through previously. The focus today is we're going back to basic set notation and we're applying sets into Venn diagrams. So I'll quickly go back and redefine what a set is. Now, in the most basic language, a set is a collection of elements. Now, these can be both finite and infinite. Generally, because we're focusing on probability for this topic, we're going to focus on finite sets, where an example would be, we can define a set as A, and within the set A, there's some certain values. So it might be that we've got the values 1, 2, 3, and 4 as elements within our set A. Every item within the set we refer to as an element, and when we're naming sets, we use capital values. An example of some infinite sets could be all real numbers, so that's everything from negative infinity to positive infinity. Could be integers, so that's every integer between negative infinity and infinity, and so on. There's lots of different infinite sets. Our focus is going to be on finite sets, so generally the sets that we're using will be predetermined for us. Okay, so that's all a set is. It's a collection of elements, a collection of items we group together, and we can give it some value or some name, right? The second thing that we'll talk about is set notation. So we've done complete lessons previously on set notation. You should have an idea of these symbols and terminology already, but we'll quickly go back over. So the first one is element. So we're saying here that X is an element of A. This symbol here states that it's an element. Basically, anything that's within a set can be an element. For an example, if we go back to this set A that I defined, I would be able to say something like 2 is an element of the set A. We can also look at not an element. So that same symbol with the line through it says not an element. And we could say something, again going back to our previous example, that 5 is not an element of the set A. So nice, easy terminology there. Subset is suggesting that in the set B, so in set B, all of the elements in B exist within set A. Okay, so that's basically what a subset is. If we say that B, for example, is equal to 2 and 3, so it has the elements 2 and 3 within that set, then we can definitely say that B is a subset of A, because those elements 2 and 3 do in fact exist within set A. The symbol here is the null set, and a null set is just an empty set, so it is a set with nothing in it. A universal set is a set that's been applied into a scenario, so we'll use universal sets all through our examples. So it may be that set A and B both come from the universal set. So that means that set A and B must be subsets of the universal set. Generally, that universal set is predefined in a question. I have trouble drawing this symbol, so I like to use omega. All right, so we've got a few really quick other little things. Intersections. So A intersects B here says we're looking at a set of the values that exist in both set A and B. So specifically, we're identifying the elements that exist both in set A and B. A union is a combination of all the elements in set A or set B. A complement is the elements not in set A in this case. So this symbol not A means a complement of A, and that's all the elements that aren't in A. So it's everything else. And then finally, this last one, the number of elements in A, that's generally called cardinality. And you can also write it as that. And that's basically just a count of all the values in that set. So the count of values in set A. So if I wanted to say the cardinality of A using my example from before, it would be 4 as there's 4 elements. Okay, so hopefully that's just a really quick review of the set notation that you already knew. What we're going to do is we're going to build this into Venn diagrams and apply. So Venn diagrams allow us to visually represent the interaction between sets. So most of the time we work with 2 sets, but we can have as many sets as we like within these Venn diagrams. So generally our Venn diagram looks like this. We've got room for 2 sets. Now these sets can be named anything. I'll just use A and B in this scenario. The square is the universal set, and that's all the elements that exist. So A and B must be subsets of that universal set. And then within that Venn diagram, we can list some elements. So let's say that we've got our universal set is the numbers 1 to 5. So 1, 2, 3, 4, 5. In set A, we've got the numbers 1, 2, and 3. And in set B, we've got the elements 3 and 4. So when we put all of that together, we can, first of all, it makes sense to write the elements that are in both A and B. So in this case, it's 3. So in that intersection there, the element 3 exists in both. We've got 1 and 2, which exist in set A but not in B. And then we've got the element 4, which exists in B. Now finally, because we're looking at the universal set that includes the numbers 1, 2, 3, 4, 5, the element 5 exists outside, so it's part of the universal set, but it's not in A and it's not in B. Okay, so I hope that you can see that allows us to visually explore the interaction between sets, and then we can start stating combinations of sets and so on. So if we looked at the intersection between A and B, that's a nice easy one. It is 3. If we look at the union of A and B, then again, it's nice and easy. The union of A and B is everything that exists in either A or B. So that will be the values 1, 2, 3, and 4. So they're the values that are either in A or B. You'll notice that I'm not repeating values, and that's because in sets we don't do that. So it's just a list of the individual values. Now we can also look at things like not A, for example. So not A will be everything that's not in A. So if we highlight what A is, not A is everything else. So that means not A will be the values, well, I missed something. That 3 is still part of A. So all the values that are not in A are 4 and 5. We can look at something like the intersection between A and not B. So we've already got A highlighted, not B. Let's use this yellow. So not B is everything that's not in B. And when we look at an intersection between those two things, it will just be 1 and 2, because they're the only values that are both in A and not B. So we can start being a little bit inventive here, and we can look at different combinations. So the main ones are what we've got listed there. Also, we can look at not B, and I'm sure we can work out the values in there. We can look at B and not A. That's a common one. So that's the values that are in B and also in not A. So in this case, that would just be 4. I like to think of these ones, this A and not B, as only A. So the values that are only in A, and the values in this B and not A will be only B. So there's a bit of a whirlwind introduction. We'll go through a couple of examples now, and hopefully you'll be able to apply this pretty quickly. Okay, so first example, they've given us a Venn diagram to represent the sets A and B. We have to assume that that universal set then is simply the values 1 through to 9. So all the elements that exist in either A or B. It wants us to find A, the union. So that means we're looking at A or B, and we want to define that set. And then B, we want to look at the intersection of A and B. Right, so union-wise, we're looking at everything that exists in either A or B. So generally when we're looking at union, if we can highlight everything within those circles, then anything that's written in there is part of that union. So what have we got? We've got 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right, it's as simple as that. Nice union of those two sets A and B. The intersection is the values that exist in both. So we can do this two ways. We could go back to the two sets and go, which values exist in both? So we've got 1 here, and we've got 3, and they seem to be the only ones. Or we can go to the center of this Venn diagram, and we can look at the intersection of those Venn diagrams, and it gives us the same answer. So the intersection of A and B is 1 and 3. So hopefully that makes sense. If I asked you for not A and not B, that would be the intersection of not A and not B. Now the only common space in not A and not B will be this area outside. So not A and not B refers to the section within the universal set that doesn't include the values in A and B. In this case, it's a null set. So we could write it like that, or we could write it like an empty set. All right, so that's the first example. Hopefully pretty straightforward. Okay, so in the second example, again, we've got a universal set of natural numbers less than or equal to 20. So natural numbers must start at 1, so that means we've got the values 1 through to 20, so we can see that there. We've got two sets, A and B, and you can see that they've constructed it so that the 4 and 16 values are in the intersection, and then we've got our remaining values A and B. Now, unlike the previous example, we've got a whole lot of values within the universal set which don't exist within those subsets A and B. So we've got 2, 3, 5, 6, 7, and so on that are part of the universal set. So that refers to that not A and not B. Okay, so all we want to do is just state the following sets. So the first one, A, is not A. Now, not A is everything else except the values in A. So we can see it on our Venn diagram. It's everything except for what's in A. We could also just list out the values that aren't in A. So that means we've got 1, 2, 3, 4 is part of A, so we're leaving that out. 5, 6, 7, 8 is part of A, so we'll leave that out. 9, 10, 11, 12 is part of A, so we'll leave that. 13, 14, 15, 16 is part of A, and then we've got 17, 18, and 19. So it's quite a large set, annoying to write, but there is a complement of A or not A. When we look at the number of not A, or the cardinality of not A, then it's how many values are in this set. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the number for the cardinality of the complement of A is 15, C. I may have got those mixed around, so that apparently is C. And now I'm looking at B, which is a number in A. So that's the number of values within the set A, and we've got 1, 2, 3, 4, 5. 5 values in set A, so the cardinality of set A is 5. D, the number of the union A or B, so how many values are in that union. So we've got 1, 2, 3, 4, 5, 6, 7. So there's 7 within that union of A and B. So that means the cardinality of A or B is 7. Now, our last one is trying to be a bit tricky. It's saying the number of A or B not. Okay, so A or B not is a complement of A or B. So if I get rid of this highlight and I do it again, so we know that A or B is everything in there. So we have to do that first. So we know what A or B is. Now the complement of that means everything that isn't that. So let's highlight everything that isn't that using yellow. And that means it's the same as that not A and not B. So here we can say that not A and not B is the same as A or B not. Those two things are the same. So how many values do we have out there? So we'll go n of A or B not. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the cardinality of that is 13. Hopefully that makes sense, that jump from determining the number within a set or the cardinality is an important one because that's where the majority of the questions are going to be aimed. So the last one is exactly that. They don't give us the values in the set, they give us the cardinalities or the numbers. So we've got a group of 50 students. That means the number in our universal set is 50. A total of 35 said they went to football matches, the movies, or both. So that's trickily talking about the union. So it's telling us that the union of football matches and movies is 35. So it's telling us the center of that Venn diagram. Of the 22 who went to football matches, 12 said they also went to movies. So that's giving us two pieces of information. That's saying that the number that go to football matches is 22, and also the number of football matches and movies is 12. So 22 go to football matches, 12 go to both football matches and movies, and we know that 35 go to football matches or the movies. So here we should have enough information to construct our Venn diagram. Now it's always easiest to start with that center, the intersection. And then we have to be a little bit careful. So we've got football matches, we've got movies, we've got the number of our universal set, which is equal to 50. So we know it has to add up to 50. Now, how many do both? We've got 12. And we know that 22 people in total go to football matches. So we have to be careful, and it has to add up to 22. So the value that goes in here is going to be not 22, but 22 take 12. So that's important to note that the whole of the circle, football matches, has to add up to that 22. So that means that the value that are only football is 10. So 10 plus 12 adds up to 22, and we're happy. Now this whole center section must add to 35. So that means this section here is 35, take away 12, take away 10. Now normally I wouldn't write this calculation, but this is for your benefit. So that means 35 take away 22, and we're left with 13. So if we add these three up, we should get our 35, and that's right. Now the other bit of information that's left out is what is the number of not football and not movies. So it must add up to 50 all up. The middle is 35. This bit here can be calculated by going, well, if we look at the total in the universal set and we subtract the number of football or movies, which means we're looking at 50 take 35, we end up with the number that are in the universal set but don't fit into either of those sets. So there we have it. We've constructed our Venn diagram. Let's now answer the question. So how many students went to the movies but not to football matches? So that means they're asking us for the number of movies and not football. So remember, that is only movies. So we're looking for that only movies thing, which is 13. And so the number, movies and not football, is 13. Now part B, how many went to neither to football matches nor to movies? So that means we're looking for these ones outside that didn't go to either. So that means we're saying that the number of not movies and not football matches, and we know that that total is 15. Okay, so that's our last example. Hopefully that is sufficient. You'll have a chance to practice that through the exercise, and hopefully this is something that you've done before and it comes back pretty quickly. Okay, thank you.